Sorry, forgot to record. So we're just recapping what some of the stuff we did in 2D, and now how does it go in 3D. So maybe I should have a different page. So this was our dot product here. For 3D, would it be any surprise that A dotted with B, it would then be A1, A2, A3, dotted with B1, B2, B3, and that ends up being A1, B1 plus A2, B2. I'm going to get rid of that because we don't need it. Make sense? Now, we call this the scalar product. The book calls it the scalar product. I call it the dot product because it's got that big old dot there. Anyone want to know why it's called this, or tell me why it's called the scalar product? Because what is your answer? The answer is a scalar. It's not a vector, it's a scalar, hence why it's called a scalar product. Now, lovely, it's got two uses. For this one here, being -1, I go big whoop doop. Doesn't tell me a whole lot. It does tell me something if it equaled 0. Pardon? The vectors were perpendicular. Any memory? So if your dot product, I really, Ash, I'd say don't copy this down seriously because there's a whole lot of properties that I want to add to it and you'll see shortly. So A dotted with B, I've got a sheet that I'll give you. Okay, so A dotted with B, if that is the case, then A and B are perpendicular, and that's what it was for 2D, and guess what? That's the same for 3D. So great, we remembered scalar product. I said there was one use for it, there's another use for it. You're sort of going out of the order of my list, but that's okay. It was used in a formula. Oh, okay, 3 uses. Projection vector, I've got to say I'm not a matches fan of projection vectors. It's like, because it's within, but the angle between two vectors. So do you remember, if I have cos theta, A dotted with B over A, now this gives you the angle between two vectors, and it has to be that it's going out from each other, from the middle to the out. So that was really important. It couldn't have been the arrow coming in. Now, we're going to do the same thing, but instead of these two vectors being on 2D, they can just be going anywhere in space, and it's the same formula. But instead of A just being A1 and A2, it's A1, A2, A3. So everything that you did with the 2D, it's the same with the 3D for a lot of these things. Then we take it a little bit further. There was something else that we wanted to do. So if I said this, we should know what that means now. What is that? The length of A. Do you remember how we found the length of a 2D vector? Yep, so if I'm calling it A1 and A2, same thing here. This would be the square root. Instead of just A1 squared and A2 squared, it would also be A3 squared. We used the length of a vector to find something pretty useful. It had a shortcut, not ultraviolet. It's very good. Unit vector. Now, what's the definition of a unit vector? It's 1 unit in length. And how do we find the unit vector, Jules? Please pay attention. We find the unit vector, we find the length, we put it 1 over, and we times it through. Yeah? Okay, what else was important from last year? What if we had 2 points? How did we find the vector between 2 points? Seriously, I've got all of this written down for you, just refreshing your memory. I promise, it's even in colour. How do we find the vector between 2 points? So if I have the point, A is 1, 2, 3. And the other point B is minus 5, 4, 0. How do I find the vector? A, B. I bet there. Yep, so what would A, B be? B. So A, B, we have to say B take A. So it'll be minus 5, take 1, and 4 take 2, and then 0 take 3. Memories or new information? Memories, like the corners of my mind. Okay, so minus 6 to minus 3. Yeah? Anything else that we recall from years gone by? I wrote a list. We've done the perpendicular. What about how would I know if a vector is parallel?
If there's a scalar multiple.
Okay, so if I've got the vector A, a parallel vector, I'm about to do geometry too. A parallel vector would be K times A. And that means we've got it going parallel. It could be going in the opposite direction. So positive if it's in the same, negative if it's in the opposite direction. Happy? Do you remember how we add vectors? Yeah, so if I had like this and I wanted to add 1, 2, 3, it's just this plus this, this plus this, this plus this. So simple. Same with if I wanted 2A. So if I had 2 lots of A, I've got A is here. What does 2A look like? Right, twice as long. And the whole vector addition stuff, so if I had 2A plus B, we've sort of been doing that with the complex numbers and the vector stuff anyway. So that's okay. There was one big thing though. If I had this vector, so I've got A, if I've got this one. So let's say that's 4 and this is 2. How would I write this vector? What point am I trying to make here? You cannot, so do not write it as A over 2. That is poor form. Okay, so simple notation. We're good? So what I thought we would do today, I'll give you the summary of all this stuff because especially with our dot product, there's some properties there that we want to play around with and that we need to know with the dot product. Simple things like A dotted with A gives you that. There's things where you've got A dotted B, dotted C, and so on and so forth. So we will have a look at that and we're going to work our way through the review questions. I know we're already at the review of chapter 5. And we'll see how we go. I think we'll be okay. So the first thing we're going to do is have a look at how do we plot points, and you can do it if you want to, but you could just look if you so desire. Oh, let's do it together. So we've got X, Y, and Z. Draw your axes. Number 2, find K, given that those vectors are unit vectors. So you already told me something before. What was so special about a unit vector? Yeah, it has one unit, and when we say it, what is it? Its length is 1. So basically we're saying find the length of that, and it has to equal 1. So that squared plus that squared plus that squared equals 1, and away we go. Huzzah? All right. This one, even, young ones, if we sort of give this to them, they could try and suss this out just by solving tops and bottoms and middle. So start and call out if you get stuck. 1. So I'm not going to put 1 squared, I'm just putting 1. And now it's just the game of, can we get K by itself? How many solutions for K are we expecting? Right, why? Because we know that when we square root something, we can have the plus or the minus. And as you are doing J, what's the bit that you have to watch out for in B? That you think some people might make a little bit of an error. Yes, very good. Jay, you threw your voice. So just remember, be careful with that. That is actually 3k squared, which is not the same as 3k squared. And if you wrote 3k squared and then it equaled 9 squared, you actually technically be wrong. So that's not the one we want. This is the one we want. Get it? Or did that confuse people? Sorry, I think I'm forgetting to record. So, yep, we're going distance unit vector is equal to 1. So it means this squared plus this squared plus this squared equals 1 squared, which is just 1. And then we solve. We know that we're expecting 2 solutions because when we square root, we can get a plus or a minus. Thing to remember with B, right, is don't forget that you have to have that in brackets. And away you go. So we're doing the review questions from 2 to 13. Yeah, okay. Yeah, what they're doing for this one? Yes, Jay?
I am multiplying the outside to the inside of each of them. And then I'm going to do like substitution or something next.
Yeah. So for the top line, you'd have what? 3 plus 2a, take b, and that has to equal 4. The middle one, we will have minus 6. Ooh, a times 0 is nothing. Minus and a minus is a plus 1 equals c, so that's nice. We're going to be able to get our c value. And then do the last one. So what have we got? We've got minus 3 plus 6a minus minus is plus 4 equals 7. And Jay was on the money there where he's going, you might have to do simultaneous, but this was very pleasant because it's given you to see, you'll be able to find A and then just sub it back in. What happens if each one of them had an A, a B and a C? Yeah, at the moment you would go your calculator, simultaneous equations. And I think I asked that you did row operations last year, did you? So we will be applying those later on to indicate solutions of planes. Work through 6 on the board and 5 we don't have to actually do. So we're now doing 7. So how could you find the vertices of triangle ABC, which is a right angle at B? Find the values of C. So a couple of ways that you could do it. You could, I think long-winded would be to find the distance to see if it's Pythag, but when it's right angled, aka perpendicular, but how do you know? Oh, it's right angled at B. Okay, so nice helps if you read it. So it means we've got, well, I won't draw it that way. We've got A, we've got B, and we've got C. So if you can find AB, and you can find BC, their dot product should equal 0, and within one of these, or maybe both of them, I can't, what was the question? You might include, no, only one of them will have that C value, so should be able to solve for C. While we're on that, if I flick down to 13, what would you do for that? Same thing. Find T, given that are perpendicular, so you're going to do the dot product equals 0. Agreed? Question 11, that's working your way through using the formula. Now, if you wanted to, if you couldn't remember how to use the formula, work out the dot product, beautiful, work out the lengths. So, grab your calculators. Okay, so just to find the angle between two, we're looking at this and I've asked you to go to your calculator. So, going to our calculator, it's been a while, so we're going to go option. We've got matrices, vectors, and let's investigate some of these things. Now that's to do with actual matrices, but if you press the more, oh okay, and go more again, you can see we've got vector, we've got dot product. I mean, if you have to use your calculator to work out the dot product between two vectors, I think there's an issue. Cross product is something that we're going to look at shortly. Oh, angle. Angle between two vectors. Let's try that one. So we're going to press F4. Do you remember using this at all? Okay. That's okay. Now we know. Seriously, 2D shouldn't need to go here. 3D, it's just a little bit tiresome and you can do it really quickly and check. But you might find that this is a pain in the butt because how are we meant to enter our vector in now? So we go exit, exit. Because now we've got math. We press math, F1 vector, and we can see you can choose your dimension, and it's a 3 by 1. So we're going to pop our vector in. I'm just going to pause it to check if I have to do that again. So we're going to pop in 2, 3, minus 1. So 2, enter. Oops. You'll learn this, so you don't have to press enter every time. So it's 2, 3, and then put your arrow key, minus 1. And it's always good fun, comma. Have you already done this, Ash? You're ahead of me. Minus 1, 0, 2. Obviously, we can say, show your steps, but you can always use your calculator to check. Huzzah, 118. There's the baby. You can see we've even got the unit vector. Again, probably more of a hassle to use it on the calculator than to actually just do it by hand. Ooh, normal vector. Who knew that was there? Anyway. So sorry, this in a little bit on Thursday, you're working your way through. How do we prove that 1, 2, 3 points are collinear? Now, my year 10s are doing slope at the moment, and they'll have a question like that in 2D. So how do they prove it with slope? Yeah, so you'd work out the slope from P to Q, Q to R, and so on. This is vectors. So we'd do the same thing. We'd work out the vector from P to Q. We'd work out, now J might work out the vector from Q to R. Alexandria might work out the vector from P to R. It doesn't matter as long as you've got 2. And one will have to be a multiple of the other. Okay? Because if you think about collinear, these 3 points are not collinear. Okay? But 1, 2, 3, these 3 points are collinear. So P to Q will be a factor or a multiple of P to R or Q to R. Make the sense? So I will be quiet 5 minutes and then we're going to do cross product before we leave. So we're trying to do all of these up to a 3. Thank you all. To give you something to do when it's nice weather on Thursday and we miss our lesson, obviously you're going to try and finish those review questions, only up to 13 please. And the one new thing that we're doing today that you didn't do last year is a thing called the cross product. And we've come across the dot product, now we're doing the cross product, and you're going to have a decision to make. You probably will go with the shortened version, but anyway, I'll stick with my long-ended version. So if we have 2 vectors, you can read here, the vector product, it's going to help us find a vector that is perpendicular to 2 other vectors. So as an example, if I have one vector going here and one vector going here, I'm going to have one that goes up and it's going to be perpendicular to the other 2. So can you imagine that that's 3D? One going here, one going there, and this one's going up. So it's like I've got on the table here, one here, and I find this vector that goes up. That eventually will help us to find the equation of a plane that those other 2 vectors are lying in. Anyway, so to do that, there's a formula which is derived from the proof that they show you there, and it's this. So if you've got the 2, I am old school and use this. And hopefully you might also use this because you did the determinants last year. So remember the determinant of, do you remember the determinant of a 2 by 2 matrix? Yep. So the determinant of a 2 by 2, so if you've got A, B, C, D. The determinant is represented by the straight lines, and that becomes just AD minus BC, correct? If I then want to find the determinant of a 3 by 3, so I say I, J, K, and then I can go A, B, C, D, E, F. To find the determinant, did you do 3 by 3?
Yeah, it was I.
So we go I, and then you break it up, and I'm going to go here, here. So it's B, C, E, F. I'm breaking the mold from the book. And then to get the J, right, you wrap around. So you go this way and then this way. So it's C, A, D, F. If you kept it in the same order as A, C, and D, F, then that would have to be a minus there. I just like to have everything plus. And then for the last one, we go K, and because I'm using K, then I have that one there, A, B, D, E. The determinant of this is the coefficient for your I. The determinant of this is the coefficient for J, and the determinant of this is the coefficient for K, and that gives me my vector. But you are by all means entitled to write that down, the green one, write that down on your help sheet, and then just go forth. So A2, B3, A3, B2. It's basically summarising this in a formula. I'm not overly confident myself. I don't know why. I can't convert that very well. I have to have the formula to look, whereas I don't have to look up this formula at all. I can just do it. But that's because I've done it for a few years. So that is us, and one of the new things that you are going to have a look at to find the the cross product. Okay? They've done it the way I would do it, except again here, instead of a minus, I would have a plus, and it would be 3, 4, damn it. It would be 3, 4, and 1, 2. Like I switch them, and then I don't have to have the minus. Make a sense? So just before we go, can everybody see, can they find the cross product on their calculator? So go back to normal again. Do you remember how to get there? Option, vector, more. Oops, too much more. Oops, damn it. Went too far. And there's your cross product there. Okay, so once again, option, matrices, 1, 2. Cross product. And then how do I get my matrix in again?
Exit.
Right, exit, math, and then we want to go matrices 3 by 1, enter the thingies, and you can get it. So I want you to get a little bit proficient with using your calculator, remembering where those things are. One less thing to remember. And can you have a go at 5I1? So reviews, 5I1, practicing your cross product. Just like 1 and 2, really, just using it. I don't need you to do a whole lot of that stuff. We'll do that later.